Hi, everybody. It's Professor Mitchell, and we made it. This is the last section that we cover in Math C, section 13.2 on the ellipse and the hyperbola. Remember, in the last section, we started talking about conic sections. So this is a continuation of that. And we'll start with the ellipse. An ellipse can be thought of as the set of points in a plane such that the sum of the distances of those points from two fixed points is constant. And don't worry, here's a picture. All right. So imagine taking a piece of cardboard and sticking two push pins in the cardboard and then connecting those push pins with a long piece of string. If you used the long piece of string to trace a shape with your pencil, that shape would be sort of an oval, and that oval is called an ellipse. Each of the two fixed points, which in this model are the push pins, is called a focus, and the plural of focus is foci. And the point midway between the foci is called the center. All right, so let's talk about the equation of an ellipse with center 0, 0. The graph of an equation of the form x squared over a squared plus y squared over b squared equals 1 is an ellipse with center 0, 0. The x-intercepts are a0 and negative a0, and the y-intercepts are 0, b, and 0, negative b. And I just want to point out that this equation is very similar to the equation of a circle. If you replaced both a and b with r, you would get x squared over r squared plus y squared over r squared equals 1, which is the same thing as x squared plus y squared equals r squared. So that's a circle with center 0, 0 and radius r. All right, so for our first example, we will graph x squared over 4 plus y squared over 9 equals 1. So what we're going to do is note the values of a and b. A is 2. Remember, it's x squared over a squared. So a squared is 4, which means a is 2. And b squared is 9, which means b is 3. So that means, first of all, we know the center is 0, 0. We're going to talk in a few minutes here about what the equation looks like when the center is some other point. The x-intercepts are 2, 0 and negative 2, 0. Remember, a0 and negative a0. And the y-intercepts are 0, 3 and 0, negative 3. So if you plot those 4 points and connect them with an oval, you will get the graph of your ellipse. All right, for the next example, we have 4x squared plus 9y squared equals 36. So what we want to do with this one is put it in the correct form. And we're going to do that by dividing every term by 36. We need that number on the right-hand side to be 1. So if you divide everybody by 36, you end up with x squared over 9 plus y squared over 4 equals 1. So very similar to the last problem. The center is 0, 0. A is 3 because a squared is 9. And b is 2 because b squared is 4. So I think this is just the same exact ellipse that we looked at in the last example, but it's been flipped sideways. The x-intercepts are 3, 0 and negative 3, 0. And the y-intercepts are 0, 2 and 0, negative 2. So there's the graph of that ellipse. All right, and then if you want to shift the center to some other point, this is like what we did back in chapter 8. Replacing x with x minus h is going to shift the graph h units horizontally. So for now, I'll assume that that h is positive. So that would shift it h units to the right, and replacing y with y minus k would shift it k units up. And then, of course, if either h or k is negative, for example, if h was negative 2, you would have x minus negative 2, which would appear as x plus 2. Okay. Now, you have to deal with the values of a and b a little differently. These are no longer going to represent your x and y intercepts. How it's going to work, and you'll see this in the next example, is you start with the center, and then the value of a is going to tell you how many units to move to the right and to the left to get sort of the left and right endpoints of your ellipse. And then the same thing with b. Starting at the center, you'll get the other points on your ellipse by moving b units up and down. All right, so for example, x plus 3 squared over 25 plus y minus 2 squared over 36 equals 1. The center is at -3, 2. Notice it's -3 because it's x plus 3. So think of that as x minus -3. And now a is 5 and b is 6. So what we're going to do is graph the center and then count 5 units right and 5 units left to get your first 2 points. And then starting at the center, count 6 units up and 6 units down to get your other 2 points, like you see here. So here's -3, 2. We move 5 units to the left and to the right. That gives us 2 points. And then starting from the center again, move 6 units up and 6 units down to get the other 2 points. All right, so that brings us to hyperbolas. There are 2 sort of different kinds of hyperbolas centered at 0, 0. So let's start with the one on top. The graph of an equation of the form x squared over a squared minus y squared over b squared equals 1 is a hyperbola with center 0, 0 and x-intercepts a0 and -a0. So a couple things to point out about this. First of all, a hyperbola is usually easy to identify. It looks like the equation of an ellipse, except with a minus in the middle. Notice also that this hyperbola on top has no y-intercepts. There is going to be one other feature that we're going to use to draw this graph, which we'll talk about in a minute to help you get the shape of it. And then you also have the graph of an equation of the form y squared over b squared minus x squared over a squared equals 1. So notice the x and the y terms have been switched. This is a hyperbola with center 0, 0 and y-intercepts 0, b and 0, -b. All right, so excuse me, a hyperbola has a couple of asymptotes. We've talked about asymptotes before with exponential and logarithmic functions. These are dashed lines used to sketch the graph of the hyperbola. So these are going to help you determine the shape of the hyperbola. To sketch the asymptotes, you're going to draw a rectangle with vertices at a comma b, -a comma b, a comma -b, and -a comma -b. And then you draw these slanted lines through the diagonals of those rectangles, and that will help you determine the shape of the hyperbola. So we'll go through a few examples here. Starting with x squared over 9 minus y squared over 36 equals 1. So this equation has the form x squared over a squared minus y squared over b squared equals 1. So this is a graph which is a hyperbola that opens to the left and to the right. It's going to have a couple of x-intercepts. It has center 0, 0 and x-intercepts at 3, 0 and -3, 0. That's because a squared is 9, which means a is 3. The asymptotes of the hyperbola are the extended diagonals of the rectangle with corners 3, 6, -3, 6, 3, -6, and -3, -6. And that's because b squared is 36, which makes b equal to 6. So here is the graph of that hyperbola. And the next couple of examples, I'm actually going to draw them by hand on my tablet. So that might give you a slightly clearer picture of how you get this. All right, so let's do that now. Starting with 4y squared minus 25x squared equals 100. All right, so I'm going to switch over to the tablet. Okay, so the first thing I'm going to do is similar to what I did in one of the ellipse examples. We need the number on the right-hand side to be 1. So I'm going to divide everybody by 100. And that is going to make this equation y squared over 25 minus x squared over 4 equals 1. So because this equation has the form y squared over b squared minus x squared over a squared equals 1, this is a hyperbola that opens up and down like this. So now let's get the values of a and b. Those are very important. Remember, a squared is always under x squared, at least in your book. If you take me for pre-calculus, the pre-calculus book does it a little differently, but since a squared is 4, that means a is 2. And since b squared is 25, that means b is 5. So this hyperbola is going to have y-intercepts at 0, 5, and 0, -5. And the asymptotes are going to pass through the points 2, 5, -2, 5, -2, whoops. Let's try that. Well, let's just do it like this. -2, -5, and 2, -5. That's what I was trying to say. All right. So now we should be able to draw that graph. All right. Here is 0, 5. Here is 0, -5. All right. And now my asymptotes are going to pass through 2, 5. -5 and -2, -5. All right, so if we draw this rectangle, and then we draw the extended diagonals through the rectangle, be a little neater if I was doing it on an actual, whiteboard. Okay. This hyperbola is going to look something like this. We want to make sure it goes through the y-intercept and gets very close to the asymptotes without actually crossing over them. All right. So let's go ahead and look at the next example. I won't bother going over to back to the PowerPoint for this. The next example is 5x squared minus y squared equals 25. So just like in the last example, we want to make sure we get 1 on the right-hand side. So I'm going to divide everybody by 25. And that's going to give me x squared over 5 minus y squared over 25 equals 1. All right, This equation has the form x squared over a squared minus y squared over b squared equals 1. So that is a hyperbola that opens to the left and to the right. Okay, now this one's a little tricky. A squared is 5, which means a is the square root of 5. And I'm going to get my calculator here to give me a little approximation for that. The square root of 5 is about 2.2, because that's where my x-intercepts are going to be. B squared is 25, which means b is 5. All right, so this time the x-intercepts are going to be at square root of 5 comma 0 and negative square root of 5 comma 0. And the asymptotes are going to pass through the points square root of 5 comma 5, negative square root of 5 comma 5, square root of 5 comma negative 5, negative square root of 5 comma negative 5. All right, so let's see how that looks. So first, my x-intercepts are going to land right about here and here. And then the corners of my rectangle are going to be here, 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 and here. All right, so we draw that rectangle. Draw the extended diagonals through that rectangle. Okay, and remember your intercepts are here and here. So this is going to be a wider opening hyperbola. Just remember it has to get close to the asymptotes, so that's not going to happen until you get like way up here. All right, and that's going to just about do it. All right, so I hope you can see my background. I've been having a little trouble showing my face in the video the last few times. I'm not sure, some sort of quirk in Zoom. But that's going to do it for our course for this semester. Congratulations on making it all the way through, and I wish you the best of luck in all of your future math classes and all your other classes and everything that comes after that. Take care and keep in touch.